so much of the world that we have around us came from just random inquiry. I mean, if you think about we're just surrounded by all kinds of technology in this room, but if you just think about all of that technology and where it comes from, right? What are the governing equations? Some of the most important governing equations are Maxwell's equations, right? That govern electricity and magnetism. Now, Maxwell was not sitting around in 1860 going, gee, I hope they build an iPhone one day, and for this, we really should organize these equations into a beautiful form, right? It was just pure, unshackled pursuit of human imagination. And one of the greatest things, and one of the reasons why I think continued investment into basic science is so important, is that we don't know what it's going to bring. And the reason we don't know is that the thing that it's going to bring will be so much better than what we can imagine right now, right? The usefulness of useless knowledge is often underestimated. Hey, how's it going?
We've been trying to mind bend a little, but we need you to help us.
Oh my God, mind bend.
I was just saying that if we were born a couple billion years from now, we wouldn't be able to see any stars at all.
Yeah, I mean, that's right. But born too early overall.
Whoa, wait a minute. I was thinking it was kind of amazing that we're born now where we can get those images yesterday. What
Yeah,
did you think when you saw those images?
it was just too much stuff in the universe, I was just
Right.
where can I go to be left alone, right?
Really? That's what you thought?
No, I'm joking. No, it was staggering. It was a staggering set of data. I mean, it's maybe a conventional or obvious thing to say, but the image of the Carina, kind of those clouds that are so sharply being carved out by photoevaporation, it's just awesome, as in awe-inspiring. It's not the reason I kind of got into astrophysics, right? But it's one of the things that sure puts it all into context, right? I mean, I think we all feel really small,
Yeah.
right? Looking at these images, realizing all of our terrestrial concerns at the end of the day are not, just maybe not that big of a deal, when it comes to the astrophysical scale.
What was the buzz like yesterday amongst all your colleagues? Did you know this was happening? Did anyone get a scoop on this? Or what was the conversation yesterday? And how does it change how you think about your work? And what is your work?
Right. Well, so to, I guess, answer the scoop question first, on the planetary side, which, is the subfield of astrophysics where I work, one of the big kind of results was the kind of very high precision spectrum of some hot Jupiter WASP. I don't remember the exact number, 69 or something. So all these planets have, these weird license plates. And, there's a very clear detection of a water feature, water in the atmosphere. That's actually not surprising, right? There's hydrogen and oxygen in the universe all over the place. So it's not really a question. It would have been much more weird if there was no water in this atmosphere. But just looking at the sheer kind of precision of the data, that was really astounding. It's really next generation. And the other thing that was interesting is that the model didn't perfectly fit the data, right? So this is something that I like to see, because whenever this type of tension happens, right, new things are going to be there. New things are going to be discovered. And this is just the beginning, right? With the new instrument, it's always like this, where you get the first data and you think, wow, it matches what we thought in some regard, it matches none of what we thought in another regard, and it always opens up a decade worth of additional work. So that's all very, very exciting. And I think, speaking of being in a special time, right, we are in a special time. We are in a special time when we're in kind of the great era of astronomical discovery, not just with beautiful pictures, but really learning about the galactic planetary senses, right? What makes up the galactic kind of architecture of planetary systems, right? People have wondered about this question forever, and we're at an era when we're starting to really answer it.
Now, we talked about telescopes, but we also have had incredible discoveries in gravity and other instruments that are, we're going to have a neutrino detector. LHC is going to be able to, find even more things. They're all tied together. So do all those other instruments add to our ability to discover new things? And will we be using gravity in conjunction with this new telescope?
Yeah, so all of these things are really sampling a lot of the astronomical events from a different kind of part of the spectrum, right? If you think, for example, about merger of a couple of neutron stars, neutron star mergers or black hole mergers are some of the most violent events that happen in the universe, right? You could imagine looking at it with light, with trying to understand spectroscopically what's happening, right? Trying to derive that information, or you can think about hearing it gravitationally, right? Hearing the gravitational waves that come out of that event. And I'm using hearing here as, of course, an analogy, but although imperfect, I kind of like that analogy. And all of these kind of pieces of information, when they come together, start to paint a more complete picture of what actually happens in these violent events. And it's something I think about quite a bit. I mean, we are purview to actually a rather small amount of information, right? If you think about the complexity of astrophysical processes, they have no obligation to show themselves to us, right? The fact that we understand stellar interiors as well as we do, or even planetary interiors, which we actually don't understand as well as stars, right, is kind of partially a consequence of the fact that we cannot physically go inside and probe these things. So we have to get clever. And when you're a scientist, you always play this game, right, of trying to reconstruct the crime scene, so to speak, from as much information as you have access to. But oftentimes it's that those little, scratches on the wall, the little, blood splatter here and there that actually kind of reveal the full story of what really happened, in this case, billions of years ago.
Now, this particular thing, if we keep hearing the analogy, it's a grain of sand, or a grain of rice, in the distance is how much we've looked. Now, what about the Oort cloud? Will this instrument allow us to look into places where there's just darkness in a different way? There's no light to reflect. Will we be able to learn more about what kind of planet-sized things might be lurking in there?
Well, so JWST is a great tool for interrogation, but it is not a great tool for searching. So think of it like a sniper rifle, right? You're not going to look for your target using a sniper rifle. You might use something with a bigger field of view, like a pair of binoculars, but it's a great interrogation tool. So once we kind of know where to look, this is an unprecedented instrument. So when it comes to planets that lurk beyond Neptune, right, provided that such a planet, and I even think that such a planet indeed exists, right, provided that it gets discovered while JWST is in play, absolutely. And I think there's a good chance that the life cycle of JWST and the discovery of Planet 9 might overlap. It's not a given, but in case it does, absolutely, we will learn a ton of things. And it's exciting because, we think that Planet 9, this object beyond Neptune, is sort of in the 5 to 10 Earth mass range, right? This is an object which falls between that of the Earth and that of the ice giants, Uranus and Neptune, in our solar system. And we, of course, don't have an analog for that in the solar system, but as it turns out, that's the most common outcome of planet formation throughout the galaxy. So it would be a beautiful way to probe the atmospheric composition and all kinds of other stuff about planets in that mass range, which, as I said, are absent from the classical solar system that we're all used to thinking about, but are very common in orbit around other stars.
Why can't we pick this thing out? It's so big. You say it's 5 times the size of the Earth, but there's no light, nothing penetrates. Like what? Yeah. Why is it so difficult to find it? I guess you can infer it, mm-hmm, right? Because there's some mass missing somewhere in the rotations of other planets, but we can't see it. Why can't we see it?
Well, this links right back to what you were asking before of really having multiple ways to interrogate the same problem. What we see is not the direct gravitational signal of Planet 9. It's not like we're, sitting around saying, hey, gee, I'm being pulled into that direction. There must be a planet there. What we see is that the structure, the architecture of this field of debris beyond Neptune that has been arranged over billions of years requires for there to be an external gravitational sculptor, so to speak. And we see the consequences of that. Now, the question then becomes, okay, where is this sculpting, body? Where can we find it? And the answer is we can predict rather well its mass and its orbit, okay? But what we cannot tell you is where it is on its orbit. So that ends up being this big swath of sky that we have to then search. Now, I was not an observational astronomer, and I'm still not really an observational astronomer, but in connection with this whole Planet Nine thing, I started observing together with my partner in crime on all this, Mike Brown, who is a ninja at the telescope, right? He's an excellent observer. And one of the things that I've learned is that unlike theory, where, when you do theory, you're in control. It's just the equations and you're either driving this or you're either stuck. Like there is no in between. When you're doing observations, you're kind of in control, meaning the weather and the turbulence in the upper atmosphere determine how well you're going to see what you're going to see, as well as things like the telescope breaking, right? It breaks all the time, or dome wouldn't open, so all kinds of these exterior noise events happen. But these observations at the same time require you to have 3 successive perfect nights, right? If you want to say, I have searched this portion of the sky, you better look there successively on 3 different nights, and things have to go equally well, because the weakest link in the chain determines that.
All right, I have a question about that right there. That point, the repeatability factor. Are we always in the same place? And we're not, I would imagine. We're not. I mean, we're always right. So how do you even go back to that point of sky? Because we're in a different place. So not only you're having to look at the sky, but you're also having to adjust, right, the positioning of the searcher, the looker.
Yeah, Priscilla, and that's a great question. In fact, we use that. You can ask the question of, okay, how do we even detect an object in the distant solar system and know that it's in the distant solar system as opposed to being just a random star in the galaxy? Because when you're observing, all you see are little points of light, right? So how do we do it? Well, the answer is you look in the same portion of the sky, and that's not to say that you look at the exact same, part of the sky. You look at the same stars, okay? And the stars that are just randomly far away in the galaxy and the little galaxies themselves, right? They will not move relative to one another, right? They're just glued on the celestial sphere, so to speak. And it's like driving in a car on a freeway and looking at some mountain that's really, really, really far away, right? You can drive for a little bit, look to your right, the mountain's still there, right? Conversely, a tree that you're passing, right, will move in your field of view. So the reason you look at the same portion of the sky over and over again is that you use this parallax effect, that same effect as driving in a car, and to spot this little points of light that are slowly moving across the night sky. And that's why you need to do it over and over, because on the first night, you just get the reference, position, there's everything. On the second night, you can detect that motion, but it takes 3 to detect acceleration. Those 3 nights are basically there to break the degeneracy between, is this a asteroid that stopped relative to you for just a little bit, or is this really a slowly moving object?
If this planet number 9 is out there, it must be incredibly cold, no?
Yeah, it's worse than Siberia.
Well, I mean,
and I don't say that
by magnitudes, no?
Yeah. No, I think, there are models of this, and people have constructed theories of various sophistication. And the kind of characteristic number that comes out of the calculations that people have done, both in Bern and UC Santa Cruz, sort of 40 Kelvin. So that's on the chilly side.
Is that all?
Wait. For the audience, tell us how cold, we need a reference.
Okay. So
3,000 degrees below zero. What is it?
Yeah, it's hard because I don't think in terms of Fahrenheit. But if you think about Celsius, right? the difference between freezing water and boiling water is 100 degrees. Okay. Or if you say that now the temperature of freezing water is 273, okay, and the temperature of boiling water is 373, in that reference frame, the temperature of Planet 9 is 40. So pack a jacket, don't
Wow.
wear your shorts. Yeah.
I thought it'd be a lot colder.
Yeah, I did too, but I'm wondering if because it's cold, is
It
that
probably doesn't have an atmosphere, right?
well, right? And is that the elusiveness? Do we need new tools? Do we need to invent new ways to get it, to nail it?
Well, it's so a couple things. The reason it's not 3 degrees and instead 40 is because the planet itself has some heat, right? If we turned off all the lights, right, the Earth would not be 3 degrees, right? The Earth has radiogenic heating that comes out of the so it's not very much, but it's non-zero. And with respect to the atmosphere, of course, we don't know. We don't know if this has an atmosphere or not because we haven't seen it. But I think it's an okay assumption to imagine that it does, because objects that come in sort of the 5 Earth mass range typically form before the protoplanetary disk is gone. And so they do accrete hydrogen helium atmospheres, or that are kind of at a few percent level of their mass. And we see that very commonly for planets that encircle other stars. And Uranus and Neptune themselves have about an Earth mass of hydrogen and helium each. So fueled by optimism, we often make the assumption that the planet has an atmosphere. Now, do we need new tools to discover it? New tools are always welcome. And the good news is one is actually coming up online later this year. And that's the Vera Rubin Observatory in Chile. And that's being not just commissioned, I think first light is later on this year. So it's very exciting because one of the things that Vera Rubin will do well is it will be a high efficiency survey. It opens up the telescope and kind of scans the night sky every night and keeps doing the same thing. And because of that, this question of, I need to go back to the same portion of the sky kind of gets better resolved, not fully. Now, point of caution, it's in the southern hemisphere, okay? And Planet 9 is in the northern hemisphere. So it might just not reach Planet 9 because the Earth might get in the way. The Earth is not my least favorite planet,
Right.
but we'll see how that whole thing kind of unfolds. All of that said, one of the things that should come out of LSST is that the patterns that we've used to infer Planet 9's existence should come into sharper focus, right? If Planet 9 really is there, right, then these patterns should clear up, and we should be able to use that additional data to kind of make more precise predictions and refine our models. And hopefully we'll also find something that's just unexpected. Right? Whenever new instruments come online, the excitement is not so much in that we'll refine what we already know, but we will find things that we don't know and we'll be confused by them. And that will totally change the way we think.
The instrument that came online yesterday, the James Webb, how far back in time is it looking? And could you just explain why it's looking back in time, the time it takes for the light to get to us?
Yeah, it's looking back in time, really getting up there. I don't recall the exact number, but I think it's like on the order of 13 billion years, almost a full age of the universe. Now, you might say, how can you look back in time? It already happened. What's going on? And the answer is that there's a speed limit at which information can travel through the fabric of space-time. And that speed limit is the speed of light. Right? Both the gravitational signals travel at the speed of light. Light, of course, travels at the speed of light. And the whole point is that you cannot exceed it. Which means, for example, suppose, Priscilla, you and Jesse are separated by 1 kilometer, okay, or 1 mile. And you send a pigeon, okay? And a pigeon, and this is a particularly slow pigeon, so it's taking its time, only flapping its wings a couple times a second, maybe once every 2 seconds or something like that. And your image, for example, arrives with this pigeon to where Jesse is in real time, just says, wow, that's what I see. But of course, right, that image, by virtue of taking some time to get to Jesse, right, is now outdated. so to speak.
Yeah.
That's exactly what's happening when we're looking at these distant galaxies. We're looking backwards in time because they're so far away that light takes billions of years to get to us, right? So because of that, we see them at the early phases of the universe formation, which is very exciting, right? One of the things we kind of learn from high redshift, these old galaxies, or sorry, I guess very young galaxies, depending on how you look at it, is the mystery of structure formation, right? Where do galaxies come from? How did the early universe expand, et cetera, et cetera?
But wait a minute, if the images that we're seeing though have aged, presumably, right? Am I following this
Well,
the right logic?
those places are gone. Like we're looking
They're
at
gone, right? I mean,
years
it's
ago.
right. So there's that, and then how do we, or is there a way to understand accuracy? Because those images, of course, the way I look at them, like I'm trying to understand it, and so I'm trying to make it look like something I might see if I go out in to a remote part of the earth and go camping. It looked familiar, but yet extraordinary. Maybe people had. I'd love to know what people are thinking, but it felt like something. I don't even know how to say it. It's awesome, like you said.
Yeah.
But but it's gone also. But also, will the image change? I mean, how do we account for that?
Right. So all of these are fantastic questions. Without getting overly philosophical, I think it's important to here highlight the fact that it's not like there exists, a clock, right? Some universal clock, and everybody is, aging. Is just that we're not getting that information fast enough. It's more that the universe, as we see it, as we experience it, is indeed just limited by that speed of light travel time. Okay, so it's not like we can say there exists this actual reality where, and if we could only reach there and interact with it, that would be interesting. There is no way to exchange information with those galaxies as they are 13.5 billion years into their future, right? So it's a weird thing to wrap your head around a little bit, and that's kind of why relativity is so cool and so counterintuitive at times. But the observable universe and the speed limit that speed of light puts on it really limits us to that being our world. Now, you also mentioned something that I resonate with a lot, which is looking at these images. You see things that look, on the one hand, undeniably alien. On the other hand, they're also quite familiar, right? You look at the edge of the cloud in Korea, and you're like, sort of have seen something like that on the airplane, right? And it's different and yet the same. And I think that's in a lot of ways why we feel so inspired, why it's so beautiful. Astronomical images generally are so beautiful. And I think it boils down to the fact that while some laws of physics have natural scales in them, many processes are scale-free. And what I mean by that is that a lot of the same physics that will conspire to make a cloud in the Earth's atmosphere will actually operate in sort of similar ways on these scales that are unimaginably large. And so when we see their products in such alien environments, we can't help but kind of feel some form of connection to these huge, remarkable clouds of hydrogen and helium gas, because they look like something we've seen before.
Yeah.
We've seen exoplanets a couple light years away, maybe even less. Will this new telescope allow us to look at the actual exoplanet and be able to see what its atmosphere is? Because we can't really see them now, right? We can just infer they're there because there's a dimming of the light. Will this improve that?
This will both improve the dimming of the light type observations, which are the transit observations, and it will also derive beautiful information from the few planets that we can actually see directly, right? So here's the challenge with looking for planets directly, right? A planet is not very bright. And I'm not talking about its IQ. I'm talking about its, it's just how much, light it emits, right? To make matters worse, planets are often parked right next to stars. So it's kind of like saying, okay, I promise there's a firefly in New York, next to some stadium. All we got to do is find it, right? And, trying to observe from, say, LA, and trying to find that dim object. So what people do is, and this is, for example, a colleague of mine, Dimitri Maoué, is one of the world's experts on this, is trying to come up with very clever schemes to block out the sun, to block out the light from the star. These are objects called coronagraphs. And with that, they've been able to do amazing things and find planets directly, planets that orbit other stars directly. But these are planets that have to be self-luminous. Okay? So because they have to be self-luminous, these are typically young things about 100 million years or younger that still have their heat of formation. So it's a real challenge. And all of this said, JWST will definitely help with that. On the transit game, it will also be really a game changer, just because it's such a better spectrograph than what we have had before.
So this light that we've just seen will take us back to, a certain period after the universe began. But is it possible with the lensing of gravity around certain things, we can look back even further?
So we cannot look further than the Big Bang, right?
But can we look back to closer to the Big Bang? Because this doesn't look all the way back, does it?
No, it does not look all the way back, and you do kind of begin to reach a limit at some point. There's also the question of, what is the interesting thing to do as you look further and further back in time, and what question do you want to know the answer to, right? I mean, it's fun to look at the universe just for pictures, but then scientifically, you kind of want to know something about the consequences of the Big Bang, and for those types of problems, there are some of the other missions that are kind of better positioned to answer those questions, like the Planck mission that looked at the cosmic microwave background, the COBE, and things like that. So JWST will be amazing for answering certain questions, some of which we've covered, and it will be less amazing for answering other things. And one of the exciting things that we do as scientists is to figure out what questions can be addressed once the full kind of operational power of an instrument is apparent, right? A lot of the really interesting work that has come out of Spitzer, which was the predecessor of JWST, it wasn't planned, I think, originally, right? And so whenever stuff like that happens, it's a real, successful, story.
Although it's sort of always a little strange how these instruments always seem to go on a lot longer than they're supposed to, or look a lot further than it's almost as if they're trying to temper our expectations and then exceed them by accident, kind of thing.
Well, it's here I have to say I always give credit to the instrument scientists, right? The instrument scientists tend to just do a really, really good job. Right. And I think this is one of the things that I think, we should be proud of. Right. I think that as a space program, NASA is extraordinarily successful, and it's cautious. Right. It's cautious. It takes forever to build stuff, and it takes forever to launch stuff. But man, when it gets done, right, stuff works. And I think there's room for, kind of the break everything and move fast approach as well. But I think NASA is a real success, and that's I rarely rarely talk to people who are not impressed by NASA and who think that it's the space program is lame. I think
lame. Yeah.
I have a question. What would be the significance with Planet 9? Like, what do we want to find out definitively? Why is it so important to find? How does it change our life or your life?
Well, I was going to say that there'd be a lot more partying once we find, but it's not true. I'm already partying a lot. So it's just, there's not like, I mean, look, just like I would say most of astronomy, right? It's almost completely useless. I mean, there's an occasional thing that comes out from astronomy that is an immediate kind of tech transfer thing, but in an immediate sense, it is completely useless. In the long-term sense, it is and not just astronomy, but just kind of basic science, is one of the greatest things we do, right? It unshackles the human imagination to create a better world. And so much of the world that we have around us came from just random inquiry. I mean, if you think about kind of, radio, right? Or if you think about, I don't know, an iPhone or something, or I'm just surrounded by all kinds of technology in this room. But if you just think about all of that technology and where it comes from, right? What are the governing equations? Some of the most important governing equations are Maxwell's equations, right? That govern electricity and magnetism. Now, Maxwell was not sitting around in 1860 going, gee, I hope they build an iPhone one day, and for this, like, we really should organize these equations into a beautiful form, right? It was just pure, unshackled pursuit of human imagination. And one of the greatest things, and one of the reasons why I think continued investment into basic science is so important, is that we don't know what it's going to bring. And the reason we don't know is that the thing that is going to bring will be so much better than what we can imagine right now, right? And the examples of this are easy to enumerate. Let's think about quantum mechanics, right? People were not in the beginning of the 20th century hoping that someday someone will devise a quantum computer to compute something, right? They were just trying to understand the structure of the atom. The usefulness of useless knowledge is often underestimated.
Yeah. And there is that link between art and science,
Mm-hmm.
and the scientist and the poet and the thinker and the philosopher. Because right now, goodness knows, I thought you were going to say there are all these things around us that, the technology, but there's also, I think for a lot of people, at least what I was seeing yesterday, these images are a breath of something better and greater than ourselves in a world that is not is in such a difficult disarray at the moment.
Right.
This really, it's a hope, of something. It's
Totally.
an extraordinary thing.
Totally. And I think it's a really important and thoughtful point. The world is in disarray, right? But I think it's really important to also ask the question, say, and not just observe that, okay, it's in disarray, but ask, what kind of world do we want to live in? And I certainly want to live in a world where we spend, a small fraction of our time. Right? I'm not saying, let's spend all our time doing arts and crafts and writing poems, although that sounds kind of fun, right? A small fraction of our time, a small fraction of our kind of human capital doing crazy things, right? Like that's a great world, right? Where we
good crazy things.
Yeah.
Good crazy things.
That's right.
Crazy things.
That's right. We already have too many people doing just crazy things.
Yeah.
Konstantin, thank you so much.
Thank you
so much
fantastic.
to think about. We'll have to have you come back again because I still don't understand, quantum theory and all that other stuff. But
join my club. So thank you both for the wonderful conversation. And
thank you.
great beyond. Okay, bye.
Bye.